Chapter 14, Chemical Kinetics. Chemical kinetics is the study of how fast a reaction takes place. Or, that could also be said how slow a reaction takes place because, some reactions, like explosions, those are very rapid. Others, those are chemical reactions. Others, like iron rusting, that's a really slow paced reaction. So different reactions have different speeds. Also in kinetics is understanding the process of the reaction. A lot of times we see a reaction as reactants make products, but sometimes there's a lot of intermediate stuff, like the reactants first make some kind of intermediates, which then have to react to make more intermediates, which ultimately make the products we want. That is called a mechanism. And you'll do more reaction mechanisms when you get to organic chemistry. But a little fascinating background on kinetics. This starts in your book. The way the chapter opens talks about the conversion of methanol to formaldehyde. And these are organic compounds, okay? So I'm just going to use them as names. And there's other things going on in that reaction as well. But there's an enzyme that does this. And y'all have heard of enzymes in biology. What do? Enzymes help reactions go faster, right? Well, this enzyme is called alcohol dehydrogenase. So I'm just going to label it ADH, alcohol dehydrogenase. Now, let's talk a little bit about methanol. What is that commonly? Well, gasoline antifreeze is methanol. And you can go buy gasoline antifreeze at any kind of auto parts store, or even at Walmart and Dollar Generals have them. It's methanol. Methanol is also, if you've ever watched anything about moonshine, there's all kinds of shows on, that are it's funny to watch those. But when you're distilling alcohol, distilling is you're heating up a solution. Okay, so there's different things in your liquid, and you heat it up and you boil it. And when something boils, it evaporates, and then you can distill it because you have this condenser above it that'll take the gaseous vapors, and you can collect those separately in a still. Well, methanol is not the alcohol you want to drink. Okay, so let's dig back a little bit to our previous chapter. This is methanol, CH3OH. Okay, and y'all know by looking at that's going to be able to have some hydrogen bonding because of that OH group. Well, what is being distilled, the desired product in a distillation is ethanol. Okay, this CH3CH2OH, which also has hydrogen bonding. But you'll notice that because you've extended this chain a little bit, that the boiling point is going to be higher for this and lower for this. So in distillation, the process of making the alcohol, both of these are produced. So when it's distilled, the first thing that's going to boil is the methanol. And the methanol is going to be the first collection, okay? So moonshiners are supposed to throw out the first thing that drips off because that's methanol, and that's bad for you. It's poisonous. It will make you go blind if you drink it. And you might be familiar with some of the old tales of moonshiners had bad eyesight. And that's true. They did, because they wouldn't pour off the methanol. They felt like they could be losing some of their product, or maybe they didn't pour off enough of it, and so they were drinking the methanol, which is bad for you. So this boils first, and that's the first thing you collect. So you dump that, and then you can tell because of the Lewis structure of this, it's going to have to get a little bit hotter for that to boil. And so that's your desired product that you would collect. And so, y'all, I think the fascinating stuff, the practical stuff, makes the chemistry fun and helps us understand it, okay? But let's get back to kinetics. And now we know the difference between methanol and ethanol. In this process, in the body, methanol is first converted to formaldehyde, okay? And then in the next step of metabolism of this, the formaldehyde is then converted to something called formic acid, okay? And another enzyme does that, and that's alcohol dehydrogenase, okay? Do you guys see that if these were the individual steps of this mechanism, and we wanted to add these two steps together, okay, the first step plus the second step, do you see that if we produce formaldehyde in one step and use it in the next step, that the overall reaction we have here is methanol being converted to formic acid? Okay, so we don't necessarily have to talk about the mechanism and the intermediate steps, but in chemistry, sometimes it's important to understand the mechanism that's going on. Understanding this mechanism is important for the treatment of accidental ingestion of methanol, which can happen. I actually knew someone, still know him, that accidentally drank, when he was a little toddler, he drank gasoline antifreeze. And if you'll look that up, it's gasoline antifreeze. If you Google a picture of it called Heat, it's a yellow bottle. And to the toddler, it looked like Yoo-hoo, okay? And so he drank some of it. And he had to he's fine now. This was, I don't know, 35 years ago. But understanding this mechanism is in understanding how doctors treat accidental ingestion of methanol. This was actually kind of an accidental discovery, okay? The same process that you see happening here with methanol, a very similar mechanism happens with ethanol, okay? So this is drinking alcohol. There's an enzyme that converts ethanol to acetaldehyde. Misspelled it. And then that acetaldehyde is converted ultimately to acetic acid, okay? So at one time, if it was known that someone accidentally ingested methanol, y'all, the same enzyme is acting on both of these processes. But it was discovered that this enzyme preferred ethanol over methanol. And so one treatment of accidental ingestion of methanol was to have the person drink ethanol, because the enzyme would start acting on the ethanol first and would prevent the formation of this formaldehyde and formic acid, which is what causes all the damage, and the methanol could be pumped from the stomach. Okay, so that's one thing with kinetics, is understanding an enzyme's preference over one substrate, methanol or ethanol being the substrate, than another. Okay, another interesting thing about these reactions, this is since there's been a drug that's produced to do methanol, and I don't remember, there's a story in your book, it's not on the first page of opening the chapter, but there was a drug being tested for the treatment of a parasite, and I can't remember. Anyway, the FDA was experimenting with this drug for some kind of parasite infection. So, you're probably familiar with when there's a new drug introduced that you have this test group, right? We're going to test this group with the real drug, and then this group is going to take, a placebo. It's just fake, and we're going to see what the results are. Okay, well, it was noted in the group that was taking the real drug, they reported that anytime they drank alcohol, a glass of wine, a beer, whatever, they got really sick, okay? And so it was linked to, if you're taking this drug and you drink, you get really sick. What it was found out is that the drug was inhibiting this second step. And the buildup of the acetaldehyde is what was making them feel really sick. That's where your hangover is linked to. And so even though this drug was being tested as a treatment for parasitic infections, they started using that drug to treat alcoholism. And so, which is a problem. Some people, they just can't help it. And it affects so many parts of their lives. But they would give them this drug, and on one drink, they would get sick. And they were trying to deter them from drinking more by, instead of appealing, mentally and emotionally to the problems of alcoholism, just the physical pain of it. Okay, so that was just an accidental discovery of that drug. It would inhibit the second enzyme. It would cause this to build up, acetaldehyde with one drink. The person would get really sick, and maybe they wouldn't want it. Maybe that would stop them from taking another drink. So, you can read more about that in your book, and of course, there's all kinds of stuff about that on the internet, but that's interesting. Let's talk about kinetics and what we're going to do with it, because we're not always going to be looking at some of those cool reactions at this point, because first we have to get our background on how to do it. A reaction rate, how fast a reaction goes. Well, when you're measuring your speed and how fast you do something, like just traveling, right? It's miles per hour. That's your rate. So it's a distance over time is how you'd measure a speed. In a reaction, how do we measure a rate? Well, it is the change in concentration. And remember the little triangle, delta, change in, divided by the change in time. Okay, so it's a concentration change over a time change. Same thing with your speed. You're starting at one point, you're ending at another point. So it's your change in miles divided by your change in time. Your starting time would be 0. Your final time might be, it took you 30 minutes to get there. Okay. Another way of writing that would be to say the change in concentration, square brackets. In chemistry, that means concentration, divided by change in time. And a lot of time what shows up in those brackets are your components of your reaction. Okay, so like the change in, you might say the concentration of methane over change in time, because that would be what you're measuring. Okay, but it can be anything showing up in those brackets. So rates, the units of rates, concentration, a lot of times it's molarity when you're doing a rate. So it could be molarity per second, or molarity per minute, or molarity per year even. A really fast reaction, you're going to want to measure that in molarity per second. If a reaction is really slow, because you want a more reasonable number to work with, you might measure it per year. We don't see that a whole lot, but you're going to look at like per year on some radioactive isotopes. On decay, those would be per year, because some of them are really long. Yeah, some of them are really short too. But you're not going to be left with deciding what sort of time to use. In all these problems in kinetics, the time is given, but don't be confused if one time it's molarity per minute and then in another problem it's molarity per hour. Okay, it's just some kind of concentration over time. Now, molarity is used when we're measuring aqueous solutions, most commonly. But when there's a gas phase reaction, sometimes the units on gas phase reactions are going to use a pressure as concentration. And we've covered gases already, but pressure might be like atmospheres per hour, or it could be atmospheres per second. There's different units of pressure, like there's pascals, right? Pascals. Could be pascals per minute. It could be millimeters of mercury per second, per minute, etc. Okay, so y'all get what I'm saying. You can have any kind of variation of all these units, but these are all measuring the rate of a reaction. There's different times in a reaction to measure a rate, and you can read a little bit more about this in section 1 of your book. But a lot of times when a reaction starts, That's like your initial rate. And as a reaction starts, you have a whole bunch of reactants, okay? So sometimes a reaction starts really fast. And then as the reaction proceeds, see, those reactions have started getting used up. So the rate is going to change slightly over the course of a reaction, because after a certain period of time, since there's fewer reactants, the rate could slow down. And so there's an average rate over a period of time that we usually use, because the rate can change over the course of the reaction. I mean, that can be for different reasons. We typically are looking more at an instantaneous rate, which is kind of, it's an average rate over the course of time. So anytime we're talking about rate in this chapter, usually it's over the course of different times, okay? Let's look at some factors that affect reaction rate. And I'm going to talk about these. One factor that can affect the rate of a reaction is the states or the surface area of the reactants. Okay, a good example of what we've got going on here with the surface area. Of course, if you increase surface area, you can make a reaction happen faster. Like if you have a headache, you could take a capsule, a pill form of a headache medicine versus, say, Goody's headache powder. Which one of those is going to be able to get into your system faster? It's going to be the Goody's headache powder, because see, the greater surface area. How is this going to happen, and how does this relate to other chemical reactions that we might be have going on in a beaker? Well, I mean, it's the same thing. If you dissolve something in solution, you are increasing the surface area versus if you just had it in the solid form to react. Another factor, and it kind of goes along with the surface area, is going to be the concentration of the reactants. If you increase the concentration, typically you can speed up the rate of a reaction. And depending on the reaction, sometimes there's this plateau where you start to increase the concentration so much that it can adversely affect the rate of the reaction. But generally speaking, it makes sense that the more concentrated something is, the faster that reaction would happen. And we could demonstrate this in the lab with like 1 molar hydrochloric acid versus 6 molar hydrochloric acid. When you put that acid on like chalk, it starts to fizz, produce carbon dioxide. Well, the more concentrated acid, the fizzing is going to start off more vigorously than the weaker acid. Another factor that affects the rate, trying to talk too fast, the rate of a reaction is temperature. When you think about it, what does temperature do to molecules? As you increase the temperature, the movement of the molecules start to speed up. So you have more kinetic energy, right? And when the molecules speed up, the chances of them colliding and having a reaction, you're increasing the chance of collision. So, of course, generally, as you increase the temperature, you increase the rate of a reaction. And in our homes, we have a refrigerator so that we can control reaction rate. Think of it that way. Is the milk in your fridge going to spoil if it stays in there? Yes, it's going to spoil. But what if it was sitting on the counter? It's still going to spoil, yeah, but it's going to happen a lot quicker on the counter than it would in the refrigerator. Okay, so we use temperature to, slow down a reaction. Required to bake the cake. So increases the rate of the reaction. Fourth thing that could affect a reaction rate is a catalyst. And we've already talked about that in my introduction with methanol and ethanol. Because enzymes are catalysts. Catalysts speed up the rate of a reaction without being used up. And catalysts are used in lots of places. You have the catalytic converter in your car. Our car is actually in the shop right now getting that replaced. Okay, so that's what catalysts do, is speed up the rate of a reaction without being used up. And so these are some things that can affect reaction rate. In the course of a problem in this chapter, when we're doing the calculations, we're not going to be looking at the effect of the temperature and the concentration as far as a quantitative calculation of the rate. But I just want you guys to know that manipulating those can change the rates. If we are given data on concentration, let's see if I can. Okay, so I'm pulling in this data table from your book, and the first column starts time. When you start a reaction, the time of start is 0, okay? And the concentration of bromine has been measured. And then there is a rate that is measured. Somehow a rate is measured on the bromine getting used up. Notice as you proceed, as the time increases up to 400 seconds, the concentration of the bromine, of course, because that's the reactant, it starts to drop because it's getting used up. And as we said before, as the concentration of bromine drops, look what happens to the rate. The rate of the reaction is getting slower. And so if we want to calculate the rate of bromine change over the first 50 seconds, then how we could express that is we could say the rate is equal to the change in the concentration of bromine divided by the change in time. And I just said that our time was going to be the first 50 seconds. So the change in bromine, change in is always the final minus the initial. So the change in the concentration of bromine over 50 seconds would be 0.0101 molar minus 0.0120 molar. Final minus initial. At time 50, the concentration at 50 minus 0. And so the change in time is likewise final minus initial. So that would be 50 seconds minus 0 seconds. And when I calculate this and divide this out, I'll get 3.8 times 10 to the minus 5 molarity per second. Now note, I hope you punch that in your calculator, because when you enter that, you actually get a negative. Okay, so let's talk about that. There is a negative in front of this equation. Okay, why is it there? Because bromine is a reactant. So the final concentration of a reactant, the change in concentration of B divided by change in time. Okay? Okay, so let me show you how this applies, because at first glance, sometimes that doesn't make sense. Let's pretend that we don't know this. Okay? So what we know is that A is 5, we know this, that this is 5 molarity per minute. And we know that that's equal to 1/2, the change in concentration of B over time. This is the rate of B. So what I circled is your X. How do you solve for X? Don't you need to cross multiply this? So the change in the concentration of B over time is going to be 10 molarity per minute. Okay? What I just showed you in red is what we did up here when we looked at 5 and said, well, if I'm making 2 B's, it must be 10 molarity per minute. We just said that I'll make 2 B's for every 1 A. Okay? I just noticed a second ago that at some point, I hope I didn't lose some recording, guys. I'll have to watch this when I'm done and make sure, because it had paused inadvertently for some reason. So let's practice this. If you look at it just in your book at a sample problem, if we're given this reaction that 4 NO2s plus O2 makes 2 N2O5 gas. And I don't want you to get too bogged down with the words, with how it's worded, okay? Because there's different ways to word these problems. Like the word consume or use or reacting. For example, at a particular time during a reaction, nitrogen dioxide, and I'm going to spell it out. It'd be a lot easier for me to write the formula, but when I say nitrogen dioxide, you guys should be able to look at that reaction and know what I'm talking about. Nitrogen dioxide is being consumed. Consumed means what? It means it's being used. It's got to be a reactant at a rate of 0.00130 molarity per second. So let's answer the question A. At what rate is molecular oxygen being consumed? And B, at what rate is dinitrogen pentoxide being produced? Okay, it's really a lot of words for a rather simple problem. So we have one number we're given. What does that number apply to in this equation? Well, it applies to the nitrogen dioxide. So the nitrogen dioxide is 0.00130 molarity per second. So A, we want to know the oxygen, and B, we want to know the dinitrogen pentoxide. How do we figure out the oxygen? You can use either way with the fractions relating the rates, or you can, it's the same thing as following the stoichiometry. So do you see that 1/4 of this is equal to A? Because I'll make 1 oxygen for every 4 nitrogen dioxides. So the answer for A is 3.25 times 10 to the minus 4 molarity per second. Now you pause the video and solve for B. When you start the video back, you will see that if N2O5, if NO2 is 0.00130 molarity per second, then 2/4 of that is going to be the answer, because I'll make 2 N2O5s for every 4 NO2s, right? So you should have 6.50 times 10 to the minus 4 molarity per second for the N2O5.